Welcome you all. Okay, in the last module we discussed about the concepts of image enhancement using spatial domain. So in the spatial domain we directly manipulate the pixel value itself. So in the module 2 we discuss basic gray level transformation functions, that is power law transformation, log transformation and negative transformation. So after that we discuss histogram processing. So by using the histogram we can identify the characteristics of the image. So by using histogram we can do two enhancement. One is histogram equalization and other one is histogram specification. So in the histogram equalization we do histogram normalization to enhance the image. So in the histogram matching we use a reference image or target image histogram for enhancing the input image. So we consider the target image for enhancing the image. So one of the problem of histogram matching is we need to provide a proper target image. If the target image is not correct, then the output may not correct. Then we discuss two enhancement in spatial domain. One is smoothing in spatial domain and sharpening in spatial domain. Smoothing is reducing the noise. The output of smoothing will be the noise eliminated image, that is the output will be the blurred image. So usually smoothing is performed by finding averaging of the neighboring pixels. So the neighboring pixel may be a 3x3, 5x5, 7x7, 9x9. The size is always odd. Okay, then in smoothing either we can use a linear or non-linear. So in the non-linear we use order statistics filter for eliminating noise. So in order statistics filter there are mainly three types of filters. One is max filter, min filter and median filter. Next, sharpening. The sharpening operation is performed using the derivatives, first order derivative and the second order derivative. So in the first order derivative we use a equation, that is delta f divided by delta x is equal to f of x plus 1 minus f of x. So we find the difference between the neighboring pixel. So in second order derivative, delta f divided by delta x square is equal to f of x plus 1 plus f of x minus 1 minus 2 f of x. So okay, it is a 1D, one dimension. Okay, in the Laplacian we consider two direction, that is x direction and y direction. Similarly, first order derivative is also used for edge detection, that is gradient and magnitude for detecting edges. So Bell, robot and privet edge. So in this session I am going to explain a new model, a new concept, that is enhancement in frequency domain. So in order to understand the image processing concept we need to know about how we can enhance the image using frequency domain. So you are already familiar with image enhancement in spatial domain. So in the spatial domain we directly manipulate the pixel value, but in the frequency domain we modify the Fourier transform. So Fourier transform modification. So by modifying the Fourier transform we do enhancement in frequency domain. Okay, image enhancement technique classified into two categories. You already know that, spatial domain and the frequency domain. Okay, in the last model I explained you about the concepts of image enhancement using a spatial domain. Okay, in the spatial domain we directly manipulate the pixel value. In the frequency domain we do the modification of Fourier transform. So frequency domain techniques are based on modifying the Fourier transform of an image. So here the input is the frequency domain image and output is also frequency domain. So in between we convert the image into frequency domain, then after processing the output will be converted back to spatial domain. So here we do modification of the Fourier transform. So before getting to frequency domain enhancement, we discussed the concept of Fourier transform. So a Fourier transform is a periodic function can be represented by a sum of sines and cosine functions of different frequencies multiplied by a coefficient. So here you can see here there are different frequencies, frequency 1, frequency 2, frequency 3 and frequency 4. So you can see the difference between each frequency. Here the difference is at the width and height of the frequency is different. So you can see here the number of frequency in the one time width is different from one frequency to another frequency. So each frequency is multiplied with different coefficient, and after multiplying each frequency with coefficient, then we do the sum of this frequency. So here the output of adding all these frequencies. So each frequency is multiplied with different coefficient. So non-periodic function can also be represented as an integral of sines and cosines multiplied with weighted function, So here in the frequency domain, each frequency is represented by integral of sines and cosine. Okay, here this is the basic of Fourier transform. So sum of frequency. So each frequency is multiplied with coefficient. So after adding this frequency, we get the output. Okay, this is a Fourier transformation. Okay, the Fourier transformation is defined by the person Fourier. So Fourier was interested with physics of heat and developed the Fourier transform theory to model heat flow problem. So first initially Fourier transform is developed for developing a model for heat transformation. So now that Fourier transform is used for image enhancement and other processing. So here Fourier transform basic functions. Here one term is represented by one square wave. One term is represented by one square wave. Similarly, two terms represent one square wave. Two terms representing one square wave, and similarly three terms representing one square wave. So here adding of the term, So here approximating the square wave as the sum of sine waves. So here all sine waves are sum and the square wave is approximated. So the Fourier transform is like a prism. So in the prism, light wave is generated. In the Fourier transform depends upon the frequency. Frequencies are divided into different spectrum. The frequencies divided into different spectrum. So here in this the function is represented even, odd and the arbitrary function. So in an even function is represented by E of x approximately equal to f of x plus f of minus x divided by 2. Odd function is represented by O of x is approximately equal to f of x minus f of minus x divided by 2. So arbitrary function f of x can be represented by f of x is equal to E of x plus O of x. Okay, this is the basic of the Fourier transform. So in image, we perform Fourier transform either in one dimension or two dimension. So first, before processing the image in frequency domain, first we need to transform image f of x for x comma y into a frequency domain. So we can use either 1D transformation or 2D transformation. So now we consider in 1D transformation, a Fourier transform is represented by f of u of a single variable u in continuous function f of x is defined by the equation f of u is equal to integral of minus infinity to infinity f of x into e to the power of minus j 2 pi ux dx. So, I already mentioned in Fourier transform is represented by integral of function. So, integral of minus infinity to infinity, where j is equal to square root of minus 1. J is equal to square root of minus 1. The given f of u, we can obtain f of x by inverse Fourier transform. So, if you do inverse transformation of f of u, we get f of x. So, f of x is equal to integral of minus infinity to infinity f of u into e to the power of j 2 pi ux du. So, we can extend easily from 1D to 2D by using two variables u and v. So, f of u comma v is equal to integral of minus infinity to infinity f of x comma y into e to the power of minus j 2 pi ux plus ui dx dy. So, similarly, if we do inverse transformation, f of x comma y is equal to integral of minus infinity to infinity f of u comma v into e to the power of j 2 pi ux plus vy divided by vy into du dv. Okay, this is a Fourier transform with one variable and two variable. Okay, this is representation in continuous form. Similarly, we can represent in discrete transformation. Okay, discrete Fourier transform. So, in the discrete form, 1D discrete Fourier transform for discrete function f of x is represented by f of u is equal to 1 divided by m, x is equal to 0 to m minus 1 f of x into e to the power of minus j 2 pi ux. So, in the previous representation, that is a continuous representation. So, here we represent in discrete form. So, here f of x is x value is from 0 to m minus 1. So, similarly, we can also obtain f of x from f of u by performing inverse DFT, inverse discrete Fourier transform. That is, f of x is equal to summation of u is equal to 0 to m minus 1 f of u into e to the power of j 2 pi ux divided by m. So, where x is equal to 0 to m minus 1. So, here the f is generated, image is generated by the combination of illumination and reflection. So, here the concept of frequency domain follows directly from Euler's formula. So, Euler's formula is e to the power of j theta is equal to cos theta plus j sin theta. Substituting this expression into equation 5 and using the fact that cos minus theta is equal to cos theta, give us to f of u is equal to 1 divided by m summation of x is equal to 0 to m minus 1 f of x cos 2 pi x pi ux divided by m minus j sin 2 pi ux divided by m. So, where u is equal to 0 to m minus 1, thus we see that each term of the Fourier transform is composed of sum of r values. So, here summation represents sum of x values. So, x are values. So, all values means 0 to m minus 1. So, the value of f of x in term are multiplied by sine and cosine of various frequency, sine and cosine of various frequency. So the domain over which the value of f of u range is approximately called the frequency domain, because u determines the frequency of the components of the transform. So each of m terms of f of u is called frequency component of the term of the transform. So use of the term frequency domain and frequency components is really no different from the term time domain and time components. So in general, we see from equation 5 and 8 that components of the Fourier transform are complex quantities. So complex quantity contain both real and imaginary. As in analysis of complex numbers, we find it convenient sometimes to express f of u in polar coordinate. So that is f of u is equal to absolute of f of u into e to the power of minus j by u. So magnitude or a spectrum of ft, spectrum of Fourier transform is represented by f of u is equal to r square u plus I square u to the power of 1 divided by 2, 1 divided by 2. So I already mentioned f of u is derived from the combination of r and I. So r represent real and I represent imaginary. R represent real and I represent imaginary, r square and I square. So phase angle or phase spectrum of ft is pi of u is equal to tan inverse of iu and ru. I and ru. So in the image representation, I represent illumination and R represent reflection. So the power spectrum P of u is equal to f of u square plus r square u plus I square u. So here is the example of the power spectrum representation. Okay, there is one dimensional representation. Similarly, we can also represent in 2D the extension of one-dimensional discrete Fourier transform and its inverse to two-dimension is straightforward. The discrete Fourier transform of a f of x comma y of the size mn. So mn represent m rows and n columns. That is, height and width of the image is m into n. So f of u comma v is equal to 1 divided by mn into summation of I is equal to 0 to m minus 1, j is equal to 0, y is equal to n minus 1. So with respect to x direction and y direction, f of x comma y into e to the power of minus j 2 pi ux divided by m and vy divided by n. So f is equal to, for u is equal to 0 to m minus 1, v is equal to 0 to n minus 1. So to get the f of x comma y, we need to do inverse Fourier transform. So inverse Fourier transform is represented by f of x comma y is equal to summation of u is equal to 0 to m minus 1, v is equal to 0 to n minus 1 into f of u comma v into f of j 2 pi into j pi f of ux divided by m plus vy divided by n. So the magnitude spectrum is represented by f of u comma v is equal to r square u comma v plus I square u comma v into f of u comma v is equal to r square u comma v plus I square u comma v to the power of 1 by 2. Similarly, phase angle is tan inverse of I of u comma v divided by r of u comma v. So here I is imaginary, r is real. So power spectrum is represented by P of u comma v is equal to absolute square of P of u comma v is equal to r square u comma v plus I square u comma v. Okay, if we consider the first component or first pixel, f of u comma v means f of 0 comma 0 is equal to 1 divided by m x equals 0 to m minus 1 and y is equal to 0 to n minus 1 f of x comma y. Okay, the relationship between samples in spatial and frequency domain is delta u is equal to 1 divided by m into delta x, delta v is equal to 1 divided by n into delta y. So if f of x comma y is real and f of u comma v is congruent symmetry. So f of u comma v is equal to f to the power star minus u into minus v. So star indicates the congruent operation on a complex number. Okay, this is an example of the Fourier transform. So you can consider here the square size is 20 by 40 to a 20 height and 40 width white rectangle. Then the center Fourier spectrum shown after the application of log transform. So after applying log transform on the image with the center of the Fourier spectrum, here the center pixel with respect to u direction and v direction. So the separation of spectrum 0. Okay, here the transformation function is f of x comma y into minus 1 to the power of x plus 1 is equal to f of u minus y m divided by 2 and v minus n by 2. So m represent height by 2 is a middle and similarly n by 2 is also middle. So centered with respect to center of the spectrum. Okay, the filtering in frequency domain. So here when we perform filtering operation frequency domain, we consider two frequencies, low frequency and high frequency. Low frequency are slow varying components of image and high frequency faster gray level change such as noise and HS. So here in this session I'll explain the steps to be followed when we performing a filtering operation in frequency domain. So what are the steps we need to be followed when we performing filtering operation in frequency domain? So when performing filtering, we use a general term, that is g of u comma v is equal to f of u comma v into h of u comma v. So in frequency domain, the general model for filtering is g of u comma v is equal to f of u comma v into h of u comma v. Okay, g of u comma v is equal to f of u comma v and h of u comma v. So f of u comma v is DFT, discrete cosine transformation of f of x. So f of x y. So f of x y is the input image. So the input image is converted into f of u comma v. So f of u comma v is a discrete Fourier transformation output. Then h of u comma v is the filter. H of u comma v is the filter. So this is the transformation of discrete Fourier transformation of h of x comma y. H of x comma y. Okay, this is a model we use for performing filtering operation in frequency domain. Okay, let's consider the steps to be followed when we performing filtering in frequency domain. Okay, now this is the black diagram represents the steps for performing filtering operation in frequency domain. Okay, it consists of 5 steps to perform filtering operation. So it consists of 5 major steps in order to perform filtering operation in frequency domain. Okay, here the input to this filtering is the input image f of x comma y. So f of x comma y is the image is in spatial domain. Okay, image is in the spatial domain. So once we enter the image, we do pre-processing. The pre-processing is multiplying minus 1 to the power of x plus 1 x plus y, minus 1 to the power of x plus y. So x and y are the coordinates. So first, in the pre-processing step, we multiply the input image f of x comma y by minus 1 to the power of x plus 1. After that, here we compute DFT. That is discrete Fourier transformation of the input image. So here we use the pre-processed image for computing DFT. So pre-processed image is used for computing the DFT of the image. So after finding the DFT, we perform filtering operation, that is G of u comma v is equal to h of u comma v into f of u comma v. So here the multiplication of h of u comma v and f of u comma v is performed element by element. So first element, second element, third element. So here we get the Fourier, here we get the filtering output. So f is the filter mask or filter coefficient. F is the filter mask. So the filter mask is multiplied with h of u comma v. So once we multiply h of u comma v with f of u comma v, then we get the filter output. So still the output is in the frequency domain. So next we want to get this in the spatial domain. So in order to get back this in the spatial domain, we need to perform inverse transformation. So inverse transformation. So first transformation is g of u comma v is equal to h of u comma v into f of u comma v. So this is a filtering operation transformation. Then the inverse transformation, that is g of u comma v. So once you perform inverse transformation, we get the output in the form of spatial domain. Here when we are performing the filtering, initially we multiplied the input image by minus 1 to the power of x plus y. So in order to cancel minus 1 to the power of x plus 1, we need to multiply the output image by minus 1 to the power of x plus y. So in order to cancel the multiplication at the pre-processing step, we do multiplication at the post-processing step. So here we multiply minus 1 to the power of x plus y to cancel the multiplication. Then we get the output image g of x comma y. So we get the output g of x comma y. Okay. First, the input image f of x comma y is multiplied with minus 1 to the power of x plus 1. Then later, by using the output of the multiplied image is used to calculate or to compute the DFT. So here we calculate or we compute the DFT. DFT means discrete Fourier transformation of f of x comma y. So the output of Fourier transform is f of u comma v. So here either we can use one dimension or 2D. So 1D transformation or 2D transformation. Later the output of Fourier transformation, that is a DFT, is multiplied with h of u comma v to perform filtering operation. So here filtering operation may be a high pass filter or low pass filter. So high pass filter or low pass filter depends upon the h. Either we can perform high pass filtering operation or low pass filtering operation. So in frequency domain, low pass filtering operation is called smoothing filtering, and High pass filtering is called sharpening. So low pass is smoothing and high pass is sharpening. So here we perform filtering operation. So the filtering operation is h of u comma v into f of u comma v, h of u comma v into f of u comma v. Later, in order to get the output in the spatial domain, we need to perform the inverse operation. So here we perform inverse discrete Fourier transformation. So we perform inverse discrete Fourier transformation. So after getting the output, we do pre-processing operation. So pre-processing operation is required because at the beginning stage, in the pre-processing step, the input image is multiplied with minus 1 to the power of x plus 1. So in order to cancel the multiplication, in the post-processing step, we need to perform minus 1 to the power of x plus 1. So after multiplying minus 1 to the power of x plus 1, we get the output. The output is g of x comma y. So g of x comma y is the enhanced image. Okay, these are the steps, basic steps to be followed when you are performing filtering in frequency domain. So filtering in frequency domain. There are two types of filters in frequency domain. One is low pass filter and another one is high pass filter. So in the low pass filter, it attenuates all high frequency values and it allows to pass only low frequency values. So here we specified the threshold value based on the threshold frequency, or based on the cutoff frequency, the frequency will be attenuated. Example, if we said D0 is the cutoff frequency, if the frequency value is greater than D0, so all the frequencies will be attenuated to 0 and it allows only the frequency which is below D0 will be passed. So similarly, high pass filter is opposite characteristics of low pass filter. In high pass filter, it attenuates all the low frequency which are below the cutoff frequency, then it passes only the frequency above the cutoff frequency D0. So the output of low pass filter is a smoothing output. So in that the noise will be eliminated, but in high pass filter it highlights the certain frequency values. Example, edges and noise. Okay, that is about the types of filters. So low pass filter and high pass filter. So in frequency domain, low pass filter is called smoothing and high pass filter is called sharpening. So in low pass filter, once again there are three filters. One is ideal low pass filter, Butterworth low pass filter and Gaussian low pass filter. Similarly, in the frequency sharpening filter, ideal high pass filter, Butterworth high pass filter and Gaussian high pass filter. Okay, in the next session I'll explain you about smoothing filter, that is ideal low pass filter, Butterworth low pass filter and Gaussian low pass filter. Thank you.